this segment of our course, we're going to delve into the complex, yet critical subject matter of advanced Docker security. Our primary focus will be on protecting containerized applications and infrastructure. This involves deploying a comprehensive, multi-layered approach to security. You see, containers operate by packaging applications along with their dependencies. However, they also share the host operating system kernel. This dynamic, while efficient, places an increased emphasis on security, particularly in production environments. Without proper protective measures, your system could be vulnerable to a variety of threats. Now we understand that this might seem overwhelming, especially if you're new to Docker security. But don't worry, we're going to break it down and guide you through each layer of security, ensuring you have a firm grasp of how to protect your Docker environment. So let's proceed and dive into the essential.
All right, let's dive deeper into our session. Today, we are focusing on understanding the security landscape. To begin, let's explore the core concepts. Firstly, we have a attack surface. This refers to every potential point where an attacker might infiltrate or extract data from your containerized environment. It's essential to identify these points and safeguard them effectively. Next, we have isolation. Isolation is about ensuring that containers cannot negatively impact each other or compromise the host system. It's critical to set boundaries between containers to prevent potential security breaches. Finally, we have the concept of least privilege. It's about granting containers only the bare minimum access rights they absolutely need. This minimizes the risk of unauthorized access and potential damage. Now let's move on to some real-world threats. Container breakout attacks refer to scenarios where an attacker gains access to the host system by exploiting vulnerabilities in a container. Malicious image tampering involves an attacker altering the container image to include harmful components, which can lead to a range of security issues. Privilege escalation exploits are attacks where the attacker gains higher privileges than initially granted, allowing them to perform actions usually restricted. Data theft and exfiltration refer to the unauthorized extraction of data from your containerized environment, leading to potential data breaches. Lastly, resource exhaustion attacks are a form of attack where an attacker consumes all available resources, making them unavailable to legitimate users and causing a denial of service. Understanding these concepts and threats is a crucial step in bolstering the security of your containerized applications and infrastructure. On this slide, we're focusing on image security, which is essentially your first line of defense when it comes to securing your containerized environment. Firstly, it's crucial to always use trusted sources. When pulling images, stick to Docker official images or verified registries. Don't forget to verify the publisher's authenticity before deploying. This can significantly reduce the risk of pulling in malicious or compromised images. Next, it's important to keep your images minimal. By using distroless or Alpine-based images, you can reduce your attack surface. Fewer packages not only streamline your environment, but they also mean fewer potential vulnerabilities. Updating regularly is another key aspect of image security. Make sure to apply security patches promptly. You can imagine the risk involved if, for instance, an outdated Node.js image with a critical CV is left unpatched. This could potentially expose your entire infrastructure to attackers. Lastly, don't forget to exclude sensitive files. You can leverage the Docker file to prevent secret credentials and unnecessary files from being bundled into your images. This is an easy, yet often overlooked way to further secure your images and prevent unwanted data exposure. Remember, image security is just the beginning, but it's a vital part of maintaining a secure containerized environment.
The slide in focus right now, titled Running Containers as Non-Root, is dedicated to a crucial aspect of container security. By default, a container runs processes as root, which is not a safe practice. This has, in fact, led to numerous security breaches where malware has gained access to host files and systems due to this simple oversight. To mitigate this risk, the best practice is to run containers as non-root users. The code snippet provided shows how you can achieve this. The run command is used to add a new group, app group in this case, and also a new user, a user, who is a member of this group. Then, the user instruction is used to specify that the container should run as this non-root user, a user. On top of this, another protective measure you can take is to enable user namespace remapping. This technique isolates container users from host users, adding an extra layer of defense. You can enable namespace remapping with the user's remap flag. By following these best practices, you can On this slide, we're delving into a critical aspect of container security, creating a vulnerability scanning pipeline. This process plays a pivotal role in maintaining the integrity of our container environment. The concept here is straightforward. We want to make vulnerability scanning an automatic part of our CI/CD pipeline. Why? because it allows us to catch potential issues before deployment, which effectively stops any exploitation from happening in our production environments. Let's look at some of the tools you can use to achieve this. First up, we have Trivy. This is a fast and comprehensive scanning solution for containers and file systems. The command Trivy image latest initiates a scan of the specified image, helping us identify any vulnerabilities. Next, we have Docker Scout. This tool not only provides integrated scanning, but also intelligent remediation suggestions and policy enforcement. This means it doesn't just identify the problem, but also offers possible solutions. Finally, we have CI/CD integration tools like Clair and Anchore. These tools are designed to automatically fail builds when critical CVEs or common vulnerabilities and exposures are discovered. This immediate feedback loop allows us to rectify issues promptly, increasing the overall security of our container ecosystem. In essence, a vulnerability scanning pipeline is about automating the process of identifying potential risks. By integrating this process into our CI/CD pipeline, we can ensure that our container environments are as secure as possible, preventing exploitation in production. This underlines the importance of proactively managing and mitigating risks in our containerized application.
On this slide, we're diving into the concept of limiting privileges and capabilities within your container environment. It's an important rule of thumb to never run containers with a privilege flag unless absolutely necessary and extreme caution has been exercised. Now, why is this critical? Recent exploit took advantage of a misconfigured container with excessive capabilities to gain complete host access. Proper capability management could have averted such a breach. To safeguard against privilege escalation attempts, you can use the security opt equals no new privileges. This blocks any efforts to escalate privileges within the container environment. Further, it's advisable to use cap opt equals all in. Cap add equals netbind service to drop all capabilities at the start and only add what's necessary for your application. Another beneficial practice is to conduct regular reviews of container permissions. You should aim to carry out these audits quarterly and ensure unnecessary utilities like sudo are removed. Remember, these steps are designed to help you tighten security within your containers and make your applications safer and more reliable. As we move forward, we will continue to explore more strategies to fortify your container environment.
This slide is all about setting resource constraints to prevent denial of service, or DoS, attacks. Resource limits are significant when dealing with containers, as without these restrictions, a single misbehaving or compromised container can drain all host resources. This situation can lead to system-wide outages and impact all running services, which is something we'd obviously like to avoid. So what can we do to prevent this? We apply essential constraints. Firstly, we have CPU limits, which are set using the CPUS flag. For example, setting CPUS equals 1. 5 will limit the container to using no more than 1.5 of the host's CPU cores. Next, we have memory limits. This is set using the memory flag. If we set memory equals 512 M, the container will not be allowed to use more than 512 megabytes of the host's memory. We can also limit the number of file descriptors available to the container using the ulimit flag. For instance, setting ulimit nafal equals 1024. 1024 will limit the container to creating no more than 1024 file descriptors. Lastly, we have restart policies that can be applied using the restart flag. For example, restart equals on failure. 5 will configure the Docker daemon to try restarting the container up to 5 times if it crashes. These essential constraints should be applied at both Docker and orchestrator levels. This layered approach, often referred to as defense in depth, gives us an additional layer of security by ensuring that even if one level of... On this slide, we're going to discuss the importance of file system and volume security in Docker. Let's start with read-only file systems. By running Docker with the read-only flag, you can prevent tampering and malware by making container file systems immutable. This is a powerful tool against ransomware that attempts to encrypt files. As with this configuration, such attempts would be completely blocked. Moving on to temporary storage, we can utilize the tmpfs flag for ephemeral data that must be writable, but doesn't need persistence. This provides a level of flexibility while maintaining security. Lastly, let's take a look at read-only volumes. By mounting volumes with the row flag, we can effectively restrict write access. In a Kubernetes environment, you can set read-only root file system to true to achieve the same effect. Overall, these measures play a crucial role in maintaining the integrity and security of your Docker environment by controlling...
On this slide, we're delving into the crucial aspects of network security and access controls within Docker. Starting off with network segmentation, we can utilize the Docker network create secure net command. This allows us to isolate containers into separate networks. This isolation is pivotal in preventing lateral movement during attacks, essentially adding an additional layer of defense. Next, we have firewall rules. It's imperative that we restrict exposed ports and implement strict firewall policies. The rule of thumb here is to only expose necessary services externally, minimizing the chances of unauthorized access or unwarranted data leakage. Turning our attention to the Docker API, it's imperative to secure it properly. A best practice is to bind the API only to localhost. In case remote access is needed, always use TLS with certificate authentication. This ensures a secure channel of communication, safeguarding against potential cyber threats. Finally, we discussed the concept of RBAC, or role-based access control. This is a principle where we assign least privileged roles. In simpler terms, each user or process should have the minimum levels of access or permissions necessary to perform their tasks. Also, it is recommended to enable Docker Content Trust for image integrity, making sure that the images used are authentic and not tampered with. To summarize, maintaining robust network security and implementing efficient access controls are vital components of a secure Docker environment.
On this slide, we will delve into the concept of monitoring and continuous security in the context of Docker. Active monitoring is a crucial aspect of this. By deploying tools like Falco and Sysdig, we can detect suspicious container behavior in real time. Notably, this early detection strategy recently prevented a breach from spreading laterally across infrastructure, highlighting its effectiveness. The slide also outlines our suggested incident response strategy. When a security incident is detected, the affected containers should be immediately isolated or quarantined. Any compromised images should then be deleted from all registries. Next, it's important to restore systems using verified clean backups. Following this, apply any necessary patches or updates and document the lessons learned from the incident. This will help prevent similar incidents in the future and improve overall security posture. The key takeaway from this slide is that Docker security requires a defense-in-depth approach. This spans across images, containers, hosts, networks, and processes. Regular audits and continuous monitoring are essential, but so is staff education. Remember, maintaining a robust security posture is a team effort